Good morning, ladies and gentlemen. I'm Dave Crisp, and I'm going to be talking to you a little bit today about how the carbon cycle, the biosphere and the oceans responded to the 2015-2016 El Nino from a unique perspective from the observations taken by the Orbiting Carbon Observatory 2, NASA's first satellite designed to measure atmospheric carbon dioxide with the kind of resolution, coverage, precision, and accuracy to actually look for the sources that are emitting carbon dioxide out of the into the atmosphere and the sinks, the natural sinks that are absorbing it at the surface. So, OCO-2 was launched. That skipped one big slide. Okay, OCO-2 was launched in July of 2014. It's been orbiting the Earth 14.5 times a day since that time, measuring CO2 from south to north as the orbit tracks go across along a very narrow orbit track. That orbit track's only 10 kilometers wide, but we make measurements every 2.5 kilometers, so actually we measure about 1 million measurements over the Earth every day. About 80,000 of those measurements are cloud-free enough to pull out carbon dioxide. And this is what it looks like. Now, as we're moving here into March of 2015, you notice that the CO2 amounts are greener, or warmer colors are higher CO2 up here, lower in the southern hemisphere. But about now, you'll see that the biosphere is starting to actually turn on and pull that CO2 out of the air, reducing the CO2 by a couple of percent over about a 2-week period. That's the Earth breathing. It does that every year. And it's one of the most fascinating things we're looking for here, and actually watching how the biosphere sucks up that CO2. Not only does it basically suck up all of the CO2 that it emits every year, it basically absorbs half of all of the CO2 human activities emit every year. Isn't that neat? Don't you hope it keeps doing that? Well, in order to understand whether the biosphere will continue to do that, we have to make measurements at this kind of resolution, as you'll see. Once again, we're seeing high CO2 over India, over China, over the northeast part of the United States, over Western Europe. Not so much right now because it's wintertime and it's cloudy up there. And it's very, very hard to make measurements in those clouds. But as, once again, the spring advances, we see high CO2 up there to start with, but just as the trees start to grow, you'll start to see more and more blue go through initially Asia and Asia and then also North America here as the trees start to bloom and pull that carbon dioxide out of the atmosphere. We've known that that's gone on for years and years and years, but this is the very first time we've ever been able to actually measure it with this kind of resolution and this kind of coverage from space. And that's the really profound difference that we've seen. Now, I've showed some little anomalies in the CO2, and what my colleagues at the Finnish Meteorological Institution found out was all they have to do is detrend this, essentially take out that seasonal cycle, and you can make maps that look like the ones coming up here, which will actually show those anomalies or those enhanced regions of carbon dioxide much more definitely. So here we see high CO2 over northeast US, over Western Europe, over Asia, East Asia, of course. We know that those are places that emit a lot of, human activities are emitting a lot of carbon dioxide. Look what's going on over here, though. Very large carbon dioxide emissions over the southern, or North Africa. What's going on there? Well, it's biomass burning. It's basically what they use for agriculture. They burn a field, they let it grow back, they burn it again. Same thing with Southeast Asia. How do we know it's biomass burning? Our friends in Finland also correlated the CO2 emissions with nitrogen dioxide emissions seen by the OMI instrument. That's just a few minutes behind us in the same orbit track. And what OMI is telling us is that this is fossil fuel emissions, which produce a lot of nitrogen dioxide. This is biomass burning, which produces very little nitrogen dioxide. Now, what happens when we go over an individual city? One of our colleagues has been looking at individual OCO tracks. This is what an OCO track looks like over my hometown. I live right over here. And this is Caltech, by the way. And so as we go over, we see enhanced CO2 going over the basin compared to what we see just north of the basin. That's about 5 parts per million out of 400 parts per million is the kind of enhancement we see for a giant city like Los Angeles, okay? So that's kind of interesting, and we kind of knew that we're higher CO2 here, but now we can actually make these kinds of detailed measurements and start to actually estimate the amount of emissions that are coming from megacities. But when you get to a smaller city, like the one you're sitting in right now, it's a little bit harder to pull out these emissions. Los Angeles has 18 million people. You're sitting in a city now with only about 450,000, and it's very well ventilated with very good sea breezes coming off the ocean. And this is where you are, by the way. You're right over here. So as we see tracks across New Orleans, hey, first of all, it's cloudy a lot more than over Los Angeles. But when we do see those tracks, we see a much smaller enhancements in CO2. We can still pull out the emissions from the city, but they're not as obvious. One of my other colleagues decided to up the game a little bit and see if we could actually observe individual power plants. And he found under certain circumstances, this is a large power producing facility in Kansas, and we actually found out when we fly over these, we can actually simulate that plume as a simple Gaussian plume model and actually estimate values of the emissions of individual power plants from OCO2. And this is what they report to the EPA. That's what we see with a single overpass with OCO2. Pretty damn good. I don't know who is right. Now, that was useful for studying power plants in our country where we have really great information from the EPA, and it's actually published on the web. But once again, we can also use that for understanding how power plants in other places like India that aren't as well calibrated are. But while we were doing all of that and learning how well we could actually make measurements, the El Nino was starting. Warm water moving from the west to the east across the basin, and as that occurs, that warm water actually basically stops the upwelling of nutrient-rich water from depth. That water isn't only nutrient-rich, it's CO2-rich. And what we saw with buoys sitting out over the middle of the Pacific Ocean was that as the El Nino started, the CO2 emitted by the ocean surface dramatically decreased. OCO-2 and GOSAT were used to actually measure and carry out measurements over the Pacific, and we saw a decrease in the CO2 over the entire Pacific basin during this time initially as the ocean source kind of shuts down. But then a few months later, it pops up while the ocean source is still down. What's going on there? Well, to find that out, we had to use some other satellite data, so we looked up to the MOPIT instrument, which is flying in another orbit close to us, and we found out at about the same time they see a great big increase in carbon monoxide. And so we assumed that that's probably maybe from biomass burning, maybe a lot of fires somewhere. But that's only a part of the story, it turns out. And we actually had to go through a lot of extra trouble in order to actually start learning more about what actually happened during this El Nino. And it is a very complicated story. And I'm not going to go through it here because at 4:45 this afternoon, one of my colleagues, Kevin Bowman, is going to give another Hyperwall talk which goes through the gory details, shows the modeling, like Daniel just showed, that went into actually deriving the answers here. But I'll show you what the conclusions are because you're sitting here. We found that we have 3 continents. We have Southeast Asia, we have Africa, we have the Amazon. We had dramatically different things going on in these 3 areas, all of which emitted a lot more carbon dioxide into the atmosphere. In Southeast Asia, it was super hot. That's what this is, a temperature perturbation. Super dry, and we had lots of fire. And that dominated the CO2 releases from Southeast Asia. From Africa, we had normal rainfall, but it was super hot. We overcooked the vegetables. We basically increased the respiration rate over Africa substantially relative to the photosynthesis, but photosynthesis was almost normal. Then over the Amazon, it was super low precipitation, and it's been that way for a while. Relatively high temperatures. The biosphere just shut down and stopped producing, or stopped performing photosynthesis for pretty much the whole season. And so it actually released quite a bit more CO2 by respiration. So it was a much more complicated story than we ever thought it would be. We thought it would be one of those 3 things and that we would be discriminating these theories. But as it turns out, if you had a theory for why CO2 increased due to El Nino, you're right somewhere. Okay? But that's the kind of information that spatially resolved data like this gives us. Now, we've got a couple of new products. As we were trying to learn how much CO2 was coming out of these continents during El Nino, we actually came up with some real revolutions in our ability to actually pull fluxes of carbon dioxide out of the biosphere. And so our team is going to be putting out a new product here in just a few months, which actually are spatially resolved maps and regional averages of carbon dioxide fluxes as a function of time. And what we're learning from these is a lot of very interesting things. First of all, just about everywhere on Earth, what we're finding is that when we compare the results from the in situ ground-based network of carbon dioxide measurements to the space-based results between 2015 and 2016, one of the things you can see is we see from space a lot more variability than the ground-based network. Well, the ground-based network only has about 150 working stations, and it just doesn't, none of them are in the tropics where all the action is going on. So basically, we're seeing a lot more structure with the space-based data. We're also seeing that some differences in the story that's being told. The in situ data shows South America and Africa where all the action was between 2015 and 2016. We're finding all the action was, well, South America, but Siberia. We're seeing that Siberia is a weak source in the space-based data, whereas it's a sink in the in situ data. So it's completely changing. We don't know which one of those is right, by the way. We're still looking into that to make sure we understand this. The other thing I'll note is that for the ground-based data alone, we have a very shallow seasonal cycle in both the tropics, across the tropics, and also, as the next slide will show, across all of Africa, which is what I'm going to focus on here, North and South Africa. And what we're seeing is that the space-based data shows that the annual cycle of carbon dioxide, as we go through from spring, summer, winter, fall, the annual cycle of carbon dioxide seen in the space-based data is quite a bit larger than what we're seeing in the ground-based data. And so it turns out that the natural carbon cycle seen from space is actually breathing a lot more deeply. Breathing in carbon dioxide during the spring and summer, breathing out more carbon dioxide during the fall and winter than we thought it was. So this is actually an interesting new result. We're checking it now to just make sure that that's in fact true. I might be back here next year telling you a slightly different story. These are brand new results, and we're hoping that that product will be a real revolutionary product going forward. In addition, we've just reanalyzed all of the data from OCO-2 from the beginning of the mission using a new algorithm that has a number of really important improvements. And so what we're seeing here is an algorithm that provides reduced bias relative to truth metrics, such as the total carbon column observing network, which is our relevant reference thing. It also has less bias between the land and ocean. The previous product, as you went across coastlines, you often saw spurious differences in carbon dioxide. Those are gone now. Much better yields, especially at high latitudes over the ocean. So there's much better coverage over the winter hemisphere, especially over the ocean. Over land in general, and land and oceans, once again, better coverage at higher latitudes. We're beginning to work better in more cloudy regions as we reanalyze this data set. So with these updates, we're sure that this data product will continue to really open our eyes and give us a lot of new insight into how the carbon cycle works as we go forward. So with that, I'll go ahead and thank you for your attention and take any questions if I have time, Eric.